Good afternoon, everyone. Welcome to the last session of today. So my name is Paul Skrzypczyk. I'm from the University of Bristol, and I'll be chairing this session, which is focused around quantum foundations. So we have a great lineup of speakers. So I hope it will be a very exciting session. And our first speaker is Yuhao Deng from the University of Science and Technology in China, and he's going to tell us about quantum interference between independent photons. Thank you very much.
Good. Can you hear me in the back? Okay. Good afternoon, everyone. I'm Yuhao Deng from University of Science and Technology of China. And today I'm very happy to be here to share you with our recent progress on harnessing single photon techniques for quantum interference experiments. First, I'd like to show my thanks to the organizers for inviting us, and also thanks to my mentor, Chao Yang, who is invited and always looking forward to coming, but he made some problem with his visa. His passport was trapped in the United States embassy for 4 months, and he delayed his application of UK visa, very unfortunately. And also thanks to Professor Pan, who is the director of our Quantum Research Center. And also thanks to our collaborators, Marlon, Swen, John, and David. So let's move on to today's topic. The interference of light has long been a fascinating subject ever since the pioneering work of the British physicist Young on the double-slit experiment. Later, in the early 20s, another British physicist, Taylor, performed the roughly similar experiment with very feeble light down to the intensity of single photons. So this probed into first time into the quantum nature of this phenomena. And later, Dirac finally summarized from all these experimental findings that each photon interferes only with itself. Interference between different photons never occurs. So Dirac's theory is extremely successful in the first order interference experiment, which is very common in our life, from the beautiful color of the butterflies to the applications like the interfering array telescopes. However, the success met some problem in the mid-20s when Hambry, Brown, and Twist performed the so-called two-photon interference experiment, which is followed by similar experiment by Flieger and Mendel with lasers. Fortunately, this is still within the classical explanation of it's still within the classical explanation. The real problem comes when there is a HOM interference. So for HOM interference, you input a single photon into a balanced beam splitter, and you will get 50% of chance to get the photon out from either one of the two output ports. And when you input it with two photons, it is intuitively expected that there shall be 4 cases for output. The interesting thing is that when these two photons are indistinguishable, 2 out of these 4 cases interfere deconstructively, and you will get the so-called photon bunching effect. The interference here can achieve a visibility of 100%, which has no classical counterpart. And this poses a strong conceptual challenge to Dirac's celebrated statement. So here we have met some concepts like single photons and indistinguishable photons. What do we mean by this? Actually, for single photons, it can be quantified by the second-order correlation function introduced by Glauber, and it can be experimentally measured with the HBT setup. So, for example, for the top green stream of photons, they are single photons, and if you measure their second-order correlation function, which we also call G2, it reaches 0. And for coherent light, for example, lasers, its G2 goes to 1, and for thermal light, its G2 goes to 2. And next is a concept of indistinguishable photons. So indistinguishability roughly means that the photons are quantum mechanically identical in all degrees of freedom. So we know that photons do not directly interact with each other, but sometimes in some applications we want them to talk to each other. So this can be done by taking advantage of the quantum statistical principles. So for example, the HOM effect can be attributed to the boson statistics of photons. What is fascinating of HOM interference is its non-classicality. So this manifests in the visibility of this effect. We know that classical physics sets a limit of HOM interference to be no more than 1/2. But we know that if we do the HOM interference with single photons, you can actually get 100% visibility. You can also understand this non-classicality from the view of entanglement, because the output state is actually a known state with n equals to 2. And actually, you can input the beam splitter with photons of cross polarization. And in this way, you can post-select on the coincidence event and get a maximally entangled Bell state. And then you can perform the standard bio test to review the non-classicality. This non-classicality here implies broad applications in quantum information. So it is basic elements in bio measurement and projection. So it can be used in protocols like teleportation, repeater, hybrid quantum networks, and so on. And the non-classicality also implies such kind of process is hard for classical computer to simulate. So we can construct the classically hard problems from this. For example, the Boson-Sampling. And as it is closely related to the non-locality, it also plays a fundamental role in the quantum foundations. Driven by both the fundamental interests and practical interests, there have been a lot of works on demonstrating HOM interference between independent photons, including the early work of Professor Rarity, and later there are more and more such works, and they focus on more and demonstrating HOM interference with more and more independent and distant light sources. These are very good, but so far, all these previous works are limited to the man-made light sources and performed in a lab scale. So we are asking, to some extent, ambitious question: can we do it with natural thermal light source at an astronomical scale? You can easily say that this is closely related to the universality of quantum statistical principles and non-locality. So to make an analog, we know that Lincoln told us all men are created equal. And we are questioning, are all photons created equal? Or more technically, can they be indistinguishable, no matter where and how they come from in the universe? So we investigated into the possibility of demonstrating HOM interference between photons from the sun and single photons from a quantum dot in our lab. The challenges are significant. First, let's look into the sunlight property. Its quantum property just remain unknown. And it's 150 million kilometers away. It's thermal, and it has a highly complicated solar spectrum. And to observe HOM interference with our quantum dot single photons, we need these photons to be indistinguishable in all degrees of freedom, from spectrum to spatial mode and polarization, temporal information. So this set high demands on the quality of our single photon source, especially the purity and indistinguishability. So in our experiment, we use a state-of-the-art quantum dot single photon source. First, here it has a very high single photon purity measured by this G2 experiment, and its G2 is about 1%. And we also characterize its indistinguishability by measuring the Hom interference with single photons emitted with different time separation. So for one pulse separation, that is about 30 nanoseconds, the visibility of the Hom experiment is higher than 97%. And the visibility remains higher than 95% for 10 microsecond separation. So this implies that we have a near transform limited single photon source. And then we perform, we apply the quantum erasing techniques on these photons from these two dissimilar light sources. For spatial mode, we just use a single mode fiber to project the photons into the fundamental Gaussian mode. And for the spectrum, we built a filtering system composed of grating and ethylons, which can filter photons into a line width of about 1 gigahertz for both sources. And we also use PBS with very high extinction ratio to polarize these photons. And for the temporal degree of freedom, we know that sunlight is continuous in time, but the quantum dot single photons just come in pulses. So there are cases these two photons arrive at the beam splitter at a different time, and this can distinguish these two photons. So in our experiment, when we calculate the visibility, we post-select on the coincidence near the zero time delay. So in this way, most of the coincidences we registered are attributed to the photons arrive at the beam splitter almost simultaneously. But this, for this to be feasible, we need very fast single photon detection. In our experiment, we use a superconductor nanowire single photon detector with a time jitter about 20 picosecond. And you can compare it with the coherent time of the single photons, which is about 1 nanosecond. So this implies that we have access to the clear temporal interference. So here is a sketch of the overall setup. It's just a sketch. So the sunlight is collected with the help of an equatorial mount driven by a electrical motor, which can track the sun. And then the photons go through the single mode fibers and go through the filtering system, and they are polarized. And we did the same for the photons from the quantum dot. And finally, they arrive at beam splitter and detectors for interference. So far, what I have just discussed are some intuitive quantum erasing techniques that is very necessary for this experiment. But this is still insufficient to demonstrate Hom interference with sunlight. The reason is that although it has been pointed out by Jeff O that you can achieve Hom interference with 100% visibility between an ideal single photon source and strongly attenuated thermal light. But in experiment, it is not a realistic situation to have ideal single photons, because although you can have a very low G2, but it's still non-zero. So when the thermal light is too weak, the multi-photon events from the quantum dot dominates. So there is a subtle trade-off between too strong and too weak thermal light. To address this problem, we built a theoretical model modeling the dependence of the raw visibility on our experimental parameters. And here is a plot shows you the dependence of the raw visibility on the intensity ratio between the quantum dot and the sunlight. And in experiment, we just optimize these parameters to a sweet point for the highest visibility. And we also electrically gate our detectors. This is to discard the multi-photon noise from the sunlight when there comes no photons from quantum dot. Our gating is about 1 nanosecond for each pulse period. So you know that each pulse period is about 30 nanoseconds. So in this way, we can surprise the multi-photon noise from sunlight by a factor of about 13, and gives a significant increase in the raw visibility. So, before this time gating, the visibility is just a little higher than the classical limit, but with this method, we can increase the visibility to about 80%. Sorry. And with all these techniques combined together, this is what we got. You can see a remarkable homomantle dip between photons from the sunlight and a quantum dot. And as I have introduced, we calculate the visibility near the 0 time delay. So with a 20 picosecond time being, the raw visibility is about 79%. And the raw visibility remains higher than the classical limit for time being as long as 440 picoseconds. So you may wonder whether after all this, the sunlight is still thermal. So we measured the G2 of the sunlight, and the G2 is quite close to 2, which is typical of thermal light. So with this observed pronounced interference, we go on to try to generate entanglement between photons from these two distant dissimilar light sources. The method is we input the two photons into the beam splitter with cross polarization, and we then post-select on the coincidence events with photons in both output modes. And this is the measured polarization correlation in 3 polarization bases, HV plus minus L R. And we can extract entanglement state fidelity about 0.83. As we have known that our observed interference has a visibility higher than 71%. So this implies that it is possible to use this established entanglement to do biotest. And in our experiment, we use the established quantum entanglement to do this bio-experiment, and we got a violation more than 3 sigma. So what is interesting in this biotest is that the two photons involved have no common history. So our result shows that we observed a very pronounced quantum interference between photons from the sunlight and a quantum dot single photon source. And it is also a first evidence for the quantum nature of the thermal light. So besides this looking into the quantum foundations, we also focus on quantum computing with photonic systems. Here is a roadmap for quantum computation from Google. And you can see that there is a near-term milestone, quantum supremacy. Although the name is a little confusing, but it is an essential step towards scalable quantum computation. And there are 2 major candidates for quantum supremacy. One is Boson-Sampling for photonic system, and the other is random circuit sampling for superconducting system. So in our lab, we focus on Boson-Sampling. So what is Boson-Sampling? It is a quantum version of the golden board game. And because there is multi-photon interference inside the interferometer, it is believed to be very hard for the classical computer to simulate. So it is roughly an experiment that we input groups of indistinguishable single photons simultaneously into the interferometer and sample the output. The exact calculation of the output distribution is related to the permanent of a matrix, and this is a sharp P hard complete problem, and that is why we believe it's very hard for the classical computers. So in experiments, if you want to realize Boson-Sampling, first, you need a single photon source. So here is a checklist of a perfect single photon source. There are 4 requirements. The deterministic generation, this means that you need to have a push button generation of the single photons. And the second is high purity. This means that its G2 shall goes to 0. and high indistinguishability. This means that photons from the quantum dot at different time shall be quantum mechanically identical to each other. And it also needs a very high collection efficiency. So this means that you need to collect the emitted photons into a single spatial mode efficiently. And all this shall be fulfilled simultaneously, not separately, just like the loophole-free Bell test. So since 2002, people have been expecting using quantum dot as an ideal single photon source for quantum computation. But all these previous works cannot be used for multi-photon experiments. There are two major reasons. The first is indistinguishability, and the second is the collection efficiency. So first, let's look at the indistinguishability. The reason is that previous works, people usually use the above band excitation method. So the electron is excited to the above band, and then it relaxes to the first excited state, and then it comes back to the ground state and emit a single photon. So this relaxing process induces some time jitter, and the whole process is also can also suffer from charge noise, spin noise in the solid state environment. So this will decrease the indistinguishability. And for the best work, is the Hormando visibility measured can be just about 70%. This is far away from enough. So our group developed the post-resonance fluorescence method. So this means that we resonantly excite our quantum dot to the excited state, and then it emits a single photon during the falling back process. So in this process, there is no relaxing process. So the indistinguishability can be significantly increased. So this demonstrates a textbook example of two-level atom-photon interaction. So with post-excitation, in the time domain, you will observe the well-known Rabi oscillation. And in the experiment, we just set our pulse power at the pi pulse, so we can deterministically generate a single photon. And if you use continuous wave excitation and observe in the spectral domain, you will observe the model triplet. So these are all raw data from our experiment, but it's very neat. And in this way, we can achieve very high indistinguishability, which means that it is scalable for multi-photon experiment. And for the collection efficiency problem, it lies at that the refractive index of the material and the air is very different, and there will be total reflection. So it is a little hard to directly collect these emitted photons. So to address this problem, we use the micropillar cavity. You can see that the output spatial mode of the micropillar cavity is quite close to the spatial mode of a single mode fiber. So it can efficiently coupled into our collection fiber. And as a bonus, the micropillar cavity also induced the Purcell effect. So this effect will decrease the lifetime of the exciton. And this will also decrease the environmental induced noise and dephasing during this process. So it will increase the indistinguishability further. And this is so we put all this together in one quantum dot. And first we have resonant excitation, and with the excitation power set at pi pulse, we have deterministic generation of single photon. And we have high indistinguishability, and the indistinguishability remains very high even for 1,000 sequential single photons. It's still higher than 92%. And we also have very low G2, about just 1%. So now we have an excellent single photon source, and we then, for Boson-Sampling, we just use Poco-Sil to demultiplex these single photons. And So in this way we can create groups of indistinguishable single photons and input them into the interferometer simultaneously for Boson-Sampling. And in previous work, we have this 9x9 interferometer, and we did Boson-Sampling with 3, 4, and 5 photons. So this is a sketch of the overall Boson-Sampling machine. And this is a comparison between the experimental result and the theoretical prediction. So our work samps 24,000 times faster than previous works, and it is also the first time for the 4 and 5 photon Boson-Sampling. So actually, our sampling rate is higher than the early classical computer at ENIAC and Chadic. So currently, we are working on 12-photon Boson-Sampling with a 6T square interferometer, and it is ongoing. And we expect by increasing the brightness of our single photon source by a factor of 2, we can do Boson-Sampling with 20 single photons and in a 120 square interferometer. And here is a summary in an archive paper on the current state-of-the-art single photon source. And the 2 quantum dots boxed in red are from our group. And you can see they have very high efficiency and low G2 and high indistinguishability, and thus high Boson-Sampling rate. So there is still a problem, that is the scaling up of the standard Boson-Sampling. The reason is that our source has a finite efficiency. So the overall time overhead scales exponentially with the number of the photons. So to address this problem, here comes the idea of the Boson-Sampling with photon loss. So this idea, the idea is that we have n photon input modes, but we just post-select on the coincidence with n minus k photons. So in this way, we can get a combinatorial speed up, and this will bond us to the exponential disadvantage with an exponential advantage. So we did this experiment and last year, and this is Boson-Sampling with photon loss in a 16 square interferometer. And we performed Boson-Sampling with 1 photon loss for 3, 4, and 5 photon Boson-Sampling. And this is the result of the experiment comparison between the experiment result and the theoretical prediction. So for 3 photon Boson-Sampling, this photon loss method get speed up from 4 times to about 34 times with 1, 2, 3, and 4 photon loss. And the speed up we measured agrees very well with the theoretical speed up. So recently, there is another very exciting progress in our group is to use quantum dot as an entangled photon pair source. So here is a checklist for a perfect entangled photon source. It's quite like the checklist for an ideal single photon source. The entanglement fidelity, on-demand generation, extraction efficiency, and also indistinguishability for scalable use. So how do you generate entangled photons from the quantum dot? The idea is to implement the bi-exciton scheme. So we use resonant biphoton excitation to excite our quantum dot to a biphoton state. And then it just cascades to a single exciton state. And in this process, it emits 1 single photon, and then it falls back, the quantum dot falls back to the ground state and emit a second photon. So the 2 passes is actually in a polarization entangled state. And there are some challenges. The challenges is that because the first photon, the XX photon, and the X photon has different frequency. So this needs our cavity to support broadband and high extraction efficiency simultaneously. So the pillar cavity doesn't work. And we are look into a new design of cavity that is a bullseye cavity. The name is because it looks like a bullseye. And you can see that the output spatial mode is quite close to that of a single mode fiber, so we can have efficient coupling into a single mode fiber. And this is also the simulated Purcell factor, and you can see it supports broadband, which is just as we want. And so first, we did the coherent manipulation of the double-exciton state. This is just a resonant excitation of a bi-exciton state with biphoton. And so in this excitation, we just also fix our excitation power at the pi pulse, so we can also have deterministic generation of entangled photon pairs. And we also measure the G2 of the XX photon and X photon, and they are just about 1%. So we achieve both brightness and purity of the XX and X photon. And then we go on to the entanglement. So here is our measurement of the entanglement fidelity. It's about 90%. And we also measure the indistinguishability, which is essential for scalable usage. And for the XX photon, it's about 93%, and for X photon, it's also quite close to 90%. So now let's retrospect to the checklist. We know that for SPDC system, when people achieved A plus C, they can do the loophole-free Bell test. And so last year, our group achieved A plus C and D. So this enabled us to do a 12-photon entanglement. And in quantum dot, previous works have achieved A, B, C, or A, B, D. But in this work, we finally have A, B, C, and D simultaneously. And maybe this can even be used to teleport the sunlight, if you recall the previous works. So this work appeared on Physical Review Letter just 2 weeks ago. So our group also works on the SPDC source. So SPDC has long been a working house in quantum optics. Our recent progress is to make a new design of the entangled photon source to achieve 12-photon entanglement. The reform here is to decouple the spectral correlation between the Adler and the signal photon. So you can see in the graph on the right, this is measured spectrum correlation with no narrowband filtering. So this enables us to increase the system efficiency significantly, and that is why it can be used to demonstrate 12-photon entanglement. And here is our design of the entanglement source and the measured raw visibility, which is quite close to, which is 96% without narrow band filtering. And this is a setup of our generation of 12-photon GHZ state. And we also characterize this state with series of measurements, and we can extract state fidelity about 0.57, which is higher than the witness bound 0.5. So this proves that we successfully created the GHZ state. And we further go on to use this source for the scalable scatter-shot Boson-Sampling. So this protocol was proposed by researchers from Queensland and Bristol. So I don't need to go on too much on this. And we did a 12-mode interferometer and for the scatter-shot Boson-Sampling. And this is a measured similarity and distance. The similarity is about 0.98 and the distance about 0.1. And in the graph on the right corner is the likelihood test to distinguish our sampling from distinguishable sampler. So in the recent classical computers with Boson-Sampling, our group focuses on several approaches simultaneously. We do it in parallel. So including the standard Boson-Sampling with quantum dot single photon source, and Boson-Sampling with photon loss, also with the quantum dot single photon source, and also scatter short Boson-Sampling with SPDC source. So this is a plot of the 3-photon Boson-Sampling rate against the year. So all this four work boxed in dashed red are from our group. So now let's look at the property of the SPDC source. The only remaining problem is the deterministic generation. So to overcome this problem, we are now working on the multiplexing, which is what we are doing right now. And this is a plot of the number of entanglement photons against a year, and in our groups you can see sudden increase of the entangled photon numbers, and maybe we can make SPDC great again. So here are some take-home message for you. First is that our work demonstrates for the first time quantum interference between photons from the sun and quantum dot in our lab. And in raising the Boson-Sampling, our groups works on several routes in parallel. And for the standard Boson-Sampling 3, 4, 5 photons, we have a speed higher than the early classical computers, and we are also working right now on the 12-photon Boson-Sampling. And recently we also got entangled photon pair source from the quantum dot. And in the work very recently, we also achieved 12-photon entanglement. It's a PIL paper December last year. And also we use it to achieve the scalable scatter short Boson-Sampling. So thank you.
Very much for the fascinating talk. So we have lots of time for questions. Alex?
Thanks for a great talk and some amazing results. So the demultiplexing that you use for the quantum dots seems very, very high throughput. Is that your plan now to multiplex the SPDC sources using a similar Pockle cell technology, or what do you plan for this multiplexing?
For SPDC, for quantum dot single photon, it's demultiplexing with Pockle cell, and for SPDC, we use the inverse. It's multiplexing, and maybe we will not. We will also use probably the AOM to control this process.
And what kind of target efficiency are you targeting for your multiplexing?
You mean the efficiency of the SPDC?
Yeah.
So we estimate it to be more than 70%.
Okay, thanks.
Hi, thank you for the talk. In boson-sampling, classically you need n-squared modes for n photons. How do you plan to scale up the optics to reach that level?
So you mean in Boson-Sampling, the number of the mode of the interferometer shall be n squared of the number of photons. This is a good question. So currently we are, our single photons and is still in a very low number. It's just about, in previous work it's just about 3, 4, 5, and currently we are working on 12. So maybe it's we are still not considering how to scale this up very quickly. But currently, as we are comparing with classically simulable, so currently our photon number boson sampling is still can be simulated by the classical computers. So, well, for example, with a fixed number of photons and a fixed number of modes, you can calculate the sampling rate of a classical computer. So we directly compare between them. Yes, you are right. In the theoretical protocol, you need n square scale, n square modes, but we are still not in that position to think about this.
Thank you.
So not really a question, but a comment on that question. So technically, you don't need n squared modes. Huh? The assumption of n squared modes just helps you avoid the number of multi-photon outcomes, right? So if you only have APDs, then you would like to have n squared modes. But in principle, if you have photon number resolving detectors, you don't always need n squared modes, actually.
So if there are no other questions, then let's thank the speaker once again.